Okay, hello everyone. My name is Yi Huang. I'm a student of Boris Shklovskii from the University of Minnesota. Today I'm going to talk about the topics, which is, let me try to hide the video panel. How to do that? Hide video panel. Okay, now it works. So today I'm going to talk about what's the relation between activation energy and band gap in a 2D insulator. So before I talk, I would like to ask you to, if you have questions, please unmute yourself and interrupt me anytime during the talk. Okay, so this work is done by myself and my advisor, Boris Shklovskii from the University of Minnesota, and also with my collaborator, Brian Skinner from Ohio State. If you are interested in the details, you can take a look at these two papers after my talk. So to begin, let's start with the question, what's the activation energy in a 2D insulator? So here is a probably familiar to you, the band diagram of an insulator. So you have a valence band where you have electrons all occupied in this band. And you have a conduction band where electrons are empty. If you put your Fermi level in between these two bands and assumes temperature is 0, then you don't have any free electrons or holes, and you get an insulator. If you have a finite temperature, then you can have thermally excited electrons, where the concentration of electrons is proportional to the exponential of minus the distance between your chemical potential and the band edge. You can also have thermally excited holes, and the carrier density is also proportional to the distance between your chemical potential and the valence band edge. So experimentally, they can measure the resistance, and they will find the resistant peaks if they vary the chemical potential properly. And this maximally insulating state occurs when you put your chemical potential right in the middle of the band gap, such that you can minimize the carrier densities, which is the sum of electrons and holes. And often in an experiment, when they measure the conductivity, they see that it's proportional to exponential to some constant energy divided by kBt. And they define the activation energy by this constant in the exponential. And by comparing these two expressions, then you will see that naively, it seems like the activation energy is just equal to half the band gap. And such idea or such physical picture is actually related to a lot of recent experiments, because experiments want to estimate the gap using transport experiments. What they did is they can vary the chemical potential in their system, because nowadays they are dealing with 2D electron systems, so it's quite easy to tune the chemical potential by applying a gate voltage. And by doing this, they can find the maximally insulating state. And when they identify such state, they can measure the activation energy by plot a so-called Arrhenius plot, which is the logarithm of conductivity as a function of inverse temperature. And by measuring the slope of such curve, you get the activation energy. And they infer the gap by whatever the slope is and just equal to the half the band gap. So they estimate the band gap using the slope of Arrhenius plot. So a natural question to ask is how reasonable or how reliable such experimental protocol is. And there are many motivations from recent experiments, such that we think that maybe this is not reliable. For example, if we take a thin film of 3D topological insulators. So here I show you a magnetically, so they use magnetical impurities to dope the sample such that they can. Oh, I see Ilya has a question. Can you?
Hi, so is it okay to ask questions right now?
Yeah, sure.
Okay, so my quick question is the following: that in a realistic semiconductor, which is doped by any amount, you would have tail states, and then any measurement of any gap would probably tell you more about the mobility gap other than the band.
Yeah, it's a classical mobility age.
Is this going to be relevant for you? I mean, the tail states can change this energy by a lot. I mean, that's actually is used in some lasers. Semiconductor lasers use this mobility gap instead of the band gap to produce light.
Yes, we think that later I will also has something to say about it, but we think that the gap is the distance between two mobility edge in the band diagram. Does it answer your question? Because we know that tail state cannot. Tail states are localized and they cannot conduct. Yeah.
Yeah.
Okay. Thank you. So okay, let me continue. So in some recent experiments, like a 3D topological insulator, here I show you an example which is magnetically doped, and there's a magnetization gap open in the Dirac coin of this topological insulator. If you put your Fermi level inside the gap, then you can have quantum anomalous Hall. You can induce quantum anomalous Hall effect. You can also do experiments in 3D TI without such magnetic impurities by making your TI samples quite thin. Then the top surface states and the bottom surface states of your TI can hybridize with each other. And this hybridization will also opens a gap in your Dirac coin, similar to this picture. And by putting your Fermi level inside the gap, you can have quantum spin Hall effect in that case. So in either case, in both of these two cases, experiments shows the activation energy quite small than theoretical predictions. Second example is the twisted bilayer graphene near the magic angle. So we know that as specific filling factors, there's some insulating states which is related to correlation. And those insulating gaps are also of nature of correlations. Those gaps are also can be quite small. And experiments shows activation energy is also like 0.1 to 1 millielectron volts. And there are many other examples like the gap in quantum Hall states or 2D TIs. And in Bernal Bilayer graphene, you can open a gap using applying electric field. And in twisted TMD bilayers, you can also open a gap you can also change the size of the gap by applying electric field. And the problem is those activation energy you estimated or calculated using transport experiments are often much smaller than the other methods, like other experimental methods like tunneling, STM tunneling experiments, or transport experiments, or optical experiments. In those experiments, they see an energy gap more than 10 times larger than what the transport activation energy shows. So what's the problem? Why there's such discrepancy between different experimental methods? So the problem, we think, it comes from disorder. So in our previous picture, I didn't think of disorder. So basically, oh, I see Sandeep raise your hand.
I have a question. Are the system tunneling gap and the transport gap the same, or is it always, it has been always the case that there's a discrepancy?
It's not always the case, but we see that in those experiments, those examples, there's a discrepancy between them. It's not always there's a discrepancy.
Okay, thanks.
Okay, yeah. Okay, so in my previous picture, I didn't include any disorder. I think the system is completely clean, and this means the band edge of either the conduction band or the valence band are flat as a function of space. And if you put your Fermi level in the middle, then you keep inside the middle no matter what, how you change your position. But this picture changes if you include disorder. So once you include disorder can produce band bending. This band bending can be so strong that the band edge can actually cross the chemical potential and produce some holes or electrons puddles. This picture is quite old. It can be dated back to 1972 in Shklovskii and Effer's work. So if you are an experimentalist, you probably would say, well, this order is bad, but this means we have a dirty sample. What if we have a clean samples such that we can ignore the problem comes from disorder? But this problem is actually almost unavoidable, because imagine you have a 2D electron system sitting on top of some substrate. Inside the substrate, there are some charge impurities. Say it's small, it's some concentration Ni, like 1 part in a million. And we need to estimate how big is the disorder potential gamma. So to calculate that, it's actually a simple exercise of Gauss law. So you need to know what's the total number of charge inside a Gaussian cube of size R. So you calculate the net charge of impurity charge inside this cube. Well, on average, it's equal to 0, but it has some fluctuations. And the fluctuation is proportional to the square root of the total charge inside of it. The total charge is nr cube. So fluctuation is square root of nr cube. Using the charge, you can estimate what's the potential across the cube. Say the potential on this side and the potential on that side across the cube. This is just the charge divided by the dielectric constant and the size of the cube. And you see that this fluctuation of potential is proportional to the square root of your size R. This means if you increase the size of the cube, eventually you can get your potential fluctuation large enough such that it can be as large as the band edge, as the band gap. Well, in such estimation, I was ignoring the screening property of your 2D electron system. I was imagining the 2D electron system is a perfect insulator. However, this is not true. If this is true, we can indeed have arbitrary large potential fluctuation. But as I tell you that if once the band edge cross the chemical potential, you can have some electrons and hole puddles, and those puddles will screen the disorder potential. So by self-consistent calculation, so we consider both the fluctuation of charge impurities potential and the screening properties of electrons and hole puddles, we can self-consistently determine what's the fluctuation of disorder potential gamma, and also what's the screening length lambda. So to calculate that, we use a model, as I said, it's a 2D electron system. And the electrons has a dispersion relation, which is of the form of a gap-Dirac dispersion. So it has some, so it's a square root of some linear dispersion plus the band gap square. Because of this this expression contains some velocity, we can define an effective fine structure constant. And this parameter is much smaller than 1 in our model, because experimentally, for example, in 3D TI, this number is typically very small. So this is our model. We want to answer the question, what is the conduction mechanism and what is the exponential part of the temperature dependence as a function of temperature? And we focus on the maximally insulating states, which means we put the chemical potential equal to 0 in such dispersion relation. So let's summarize the result first. So our calculation shows the conductivity actually has 3 distinct regimes of conduction mechanisms as a function of temperature. At highest temperature, or the smallest inverse temperature, you have activation of carriers to the classical mobility edge. This is what Ilya mentioned in the beginning. So the activation energy is equal to half the distance between 2 classical mobility edge, or we call the band gap. Once you lower the temperature, you go to a second regime where the conduction mechanism is determined by the tunneling between nearest neighbor puddles. So this activation energy is actually related to the charging energy of one puddle. And later I will show you that because these puddles has relatively large capacitance, this means the charging energy of puddles is more in this intermediate regime. And this means the activation energy observed should be much smaller than the band gap. And once you lower the temperature further, you go to variable range hopping. And you no longer has linear inverse temperature slope. Instead, you have a square root relationship. Okay, so let me comment about the 3 mechanisms. In the highest temperature, you have activation to classical mobility edge. So in such case, although it's no longer true that you have some definite distance from your chemical potential to the band edge, because of disorder, this distance is changing as a function of position. However, by thermally excited your electrons or holes from your chemical potential to some percolation level, you can imagine that once you raise the once you thermally excited the carriers to some energy level, then suddenly the system can find a contour which can pass from one side to another side. This is the standard percolation thinking. And by thinking about the 2D percolation problem a little bit more, you can find that the symmetry of 2D percolation problem can give such an energy level exactly same as the half of the band gap. However, such percolation thinking requires the distance between electrons or hole puddles well separated from each other. This means the distance between them are quite big. And this also means we require the band gap should be much larger than this energy scale determined by disorder. However, in experiments, such condition is often strongly violated. So disorder is so strong that such that it's comparable to the band gap. And we can no longer think of such mechanism in experimental temperature range. If you lower the temperature to the second regime, then quantum mechanical tunneling starts dominate the conduction mechanism. And due to the fractal nature of puddles, the the capacitance will be enhanced because the parameter of this fractal object is actually much larger than if you naively think of a puddle of size L, you probably would think that the perimeter of it is just proportional to L, and the capacitance is also linear in L. However, because of this object is fractal, then the perimeter of it is, instead of linear in L, can be linear in L to some power larger than 1. And this enhancement of capacitance will reduce the charging energy, which is E squared divided by 2 times the capacitance. And such charging energy is related to the activation energy. Using some detailed calculation, we show that such charging energy, or the observed activation energy, is proportional to the band gap times some small prefactors. And this results in activation energy much smaller than the band gap in the intermediate temperature regime. And I should mention, we think that in most experiments, the conduction mechanism is related to this intermediate temperature regime. And finally, once we keep lowering the temperature further, we go to variable range hopping. Here I show you a plot which is for the granular metal, and a charge or an electron can hop from one granular metal to another. We think the mechanism is of first Shklovskii like expression, and the characteristic temperature is determined by some localization length psi. And this localization length will be enhanced by the disorder streams. Later I will show you. So as I mentioned, the localization length will be enhanced by disorder. How is that? How does it happen? So we think of disorder potential much larger than the band gap. This means the distance between puddles, which I indicate as W here, is actually becoming smaller if you increase the disorder potential gamma. Because if you have larger gamma, this means the slope of this curve, or the electric field corresponding to the puddles, becomes bigger. This means the distance between puddles will also become smaller. If you have smaller distance between puddles, then the tunneling action from one puddle to another puddle will also become smaller. Because of the smaller tunneling action, this means it's easier to conduct. And so if you have larger impurity concentration, you increase the disorder potential, and you can get larger conductance between puddles. And we can imagine at some critical concentration, the conductance becomes larger than E squared over H. This means the system is turned on for conduction. And the localization length starts proportional to exponential of conductance divided by some dimension is constant. If the localization length is so large such that in realistic sample, the sample size can be the sample size is actually smaller than such a localization length, then we think the system becomes almost like a metal. We cannot distinguish it from a metal or some system with exponentially large localization lengths. So in such case, we call that disorder will induce an insulator-to-metal transition in such system. So to conclude, our model predicts 3 distinct regimes of conductivity, and only in the highest temperature regime we see that the activation energy is related to the distance between classical mobility age, which is like every experimentalist think of in doing experiments. However, we think that actually for those those experiments I mentioned, like TI or bilayer graphene, maybe the conduction mechanism is related to the tunneling between nearest neighbor puddles of electrons and holes. In such case, the activation energy can be much smaller than the band gap. Okay, and if you keep lowering the temperature further, you go to variable range hopping, and you have even smaller apparent activation energy. Okay, so if you are interested in more details, you can go to these two papers. And before I end my talk, I probably would like to show you some data of experiments. So here is a plot of conductance, the logarithm of conductance as a function of inverse temperature, taken from Chang's group. And this is magnetically doped topological insulator. They observe activation energy, although it's only 3 points, maybe it's not conclusive. The slope of it, I believe it's corresponding to temperature less than 1 K. However, they theoretically predicts using some DFT calculation, they theoretically predicts the band gap should be like 30 milli-electron volts. So the difference is quite big. It's more than 100. And in this case, I take a plot from Pablo's group, who did transport experiments in the Bernal Bilayer graphene. And you already see by eye that this shape looks quite similar to what I show you in my theoretical prediction. So in the highest temperature regime, seems like the slope becomes bigger. Although in Pablo's paper, he said that he cannot conclude any activation energy from this part because he see the points is not, it's just showing exponential behavior in the beginning, so he cannot conclude any activation energy in this regime in any accuracy. So he instead look at the lower temperature regime where the slope becomes smaller, but they have more points. So they find that the activation energy related to this slope is also more than 100 times smaller than theory predicts. And finally, there's data from Kim Feimak's group where they did the transport measurement and calculate the gap related to a continuous Mott transition. So here is their activation energy, calculating using the slope of resistance. And they see that the slope can becomes smaller and smaller once they approach the Mott transition point. However, you can see that the smallest activation energy they get is like 6 milli-electron volt, and they have no data points below that. And probably this is related to disorder also. Okay, I think that's the end of my talk. Thank you for your attention.